Okay, so we're going to look at a special case of solving triangles, the ambiguous case. So just a reminder, solving triangles, this is an exercise we've been doing where for any given triangle, there are 6 relevant pieces of information, the 3 angles and the 3 side lengths. And we have explored situations where you have 3 of those 6 pieces of information, and we'll use the law of sines or the law of cosines to find the remaining 3 pieces of information. So a solved triangle is when we have all 6, we know all 3 angles and all 3 side lengths, starting with 3 of them. So there's one particular case that we call the ambiguous case because it turns out you can't necessarily solve it for one particular triangle, depending on how it shapes up. So we want to explore that a little bit. So let's get into that. So this case is called it's the side angle case, SSA. So what this means is we have 2 sides and an angle, but the angle is not between the 2 sides. Okay, so I'm going to sketch a little picture of this. Let's start by saying, let's assume that we know side A, side B, and angle alpha. Okay, so remember we're using capital letters, capital Latin letters for the side lengths and our lowercase Greek letters for the angles. Angle alpha would be the angle across from side A, angle B would be across from angle beta, and then angle gamma would be across from side C. So in this case, I can kind of sketch the situation. We don't know enough yet to get a very accurate sketch, but I can do something. So I'm going to start with angle alpha. I'm just going to put it here. Okay. I don't know, so this will represent side C. I don't know how long it is, so I'm just drawing a dashed line. I know the direction it goes in. And then I have to put side B here. Remember, this is one of our known lengths, so whatever that is, I would draw it that length. Here's B. Angle gamma will be up here, because angle beta will be out here somewhere, depending on where the other side hits. Now, across from side alpha is going to be side A, but I don't know the direction it's going in, right? So I know its length, right? So for instance, it might be this. If that was the length, we might have a triangle that looks like this, depending on the length. What we're gonna explore is how that length determines when we have more than one answer, or in some cases, no answer. So I'm not going to draw it in yet. We're going to start exploring that. What I am going to draw in, sorry, I hit my camera there. What I am going to draw in is I'm going to drop a perpendicular line from gamma, from this point, down to this line that we know side C lays along somewhere. And we'll call this H. So this is, if we had a little right triangle here, this is our height of that triangle. That's going to help us determine when we have this ambiguous case. Okay. So let's look at a few cases. Suppose side A, remember we know it, side A, let's say the length is less than H. Okay, so I'm using this paper clip. Here's side A. We don't know the angle, so it can go in any direction, but it's smaller than H. Notice, no matter what, no matter how I move this, that is never going to hit that horizontal line there that represents where side C must be, right? So this is a case where it's actually not possible. There is no triangle, okay? So if we can give problems, right, where you have that situation where this number is too small, it's below this H, that there is no triangle that would have the particular setup as given. Right? The way that usually shows up is you end up with something like sine of an angle that you're looking for is equal to a number bigger than 1, which we know is impossible. Sine is always less than or equal to 1. And so then you know you've been given nonsense. You've been given numbers that can't have a triangle and asked to find the triangle. So you get nonsense back. Let's look at the case where A equals H. All right. Well, if if this side A is exactly equal to the height, then we get this triangle. And if I try to change gamma to be any other angle, then this side A swings off of this horizontal line. There's only one point where it hits it, and that's exactly when it hits it at a right angle. And so when that's the case, we will find one right triangle. Right? In this case, you'll know you have this when you take your when you solve for. We'll see in a moment that we're going to be solving for this angle over here, angle beta, where that will lie along here. And if it turns out to be a right angle, you know you're in the case where A equals H. The next case would be A between A and B. So it's longer than the height, but shorter than this other side. We'll come back to this case. So before we come back to it, let's look at the final case, which is A greater than or equal to B. So in that case, well, if A is equal to B, we can only find, sorry, something was distracting me outside. So let's say A is equal to B, right? So I'm putting this side here. If we rotate this around, right, this will not be a triangle, right? Because we just have a line there. As we rotate it around, there's going to be some point out here. We'll end up with an isosceles triangle. All right, so we have exactly one place where it's going to hit this. As we keep rotating, there's no more. As we come back, the only other place it hits it is right there. And if A is greater than B, the same thing happens. We're out here. We swing it around. At some point, it's going to hit that horizontal line, and there's our triangle. And so we get one triangle, right? It won't be a right triangle. We'll get one triangle exactly, okay? So in that case, again, we'll get exactly one triangle where A is greater than B. And you'll know you're in this case. Remember, A and B are given, so if you see that A is greater than B or equal to B, you know that you're in this situation and you're only looking for one triangle. So now we're back to this case, okay? So we're going to examine it geometrically and then see what happens when we're actually solving solving this triangle. So now I'm finding a length that is longer than the height, but shorter than B, right? So this looks like I've about gotten it, okay? Now notice what happens here. I can arrange that like this. I know it's a little hard to see. That's longer than the height and shorter than B, but I can also swing this out somewhere over here, right? So what we end up with in this case is two possible triangles, right? I'll sketch that one in there, and we get a similar thing here, okay? So we'll get two triangles. So let's look a little closer at these two triangles, right? So I'm going to try to redraw this triangle here. And I'm going to draw this bigger triangle here, right? So this side and this side are the same, something like this. Okay, my picture's not perfect, but let's label it to make it clear. This is side B, this is side B, angle alpha. We get C, beta, beta. This is A, this is A, this is gamma. Okay. So remember, this A and this A are supposed to be the same length. I think my drawing's a little bit off, but I did a little better job over here. It's the idea that we can swing it out. Okay. And so there are two possible triangles that have this original given setup. Okay. So let's see a couple of things. So first of all, let's imagine we're going to solve this. The way we'll typically solve these, since we're given angle alpha and the side across from it, the law of sines comes to mind. This is known. And we have side B, and we can find sine beta this way, right? If you look at this equation, this is known, this is known, this is known. So B times sine alpha over A equals sine of beta. Or in other words, beta is equal to sine inverse of B sine alpha over A. Okay? Now, this is some number, right? We know B, we know A, we know alpha. This is, if we're doing a case where A is less than H, this would be when it shows up that there's nonsense, this number would be bigger than 1, and there's no inverse sign for a number that's bigger than 1. In this case, though, where A is between A and B, this is going to give us one of these two angles, but it's not clear which one at first. But we remember what sine inverse does. Sine inverse gives us an angle between negative pi over 2 and pi over 2, or negative 90 and 90 degrees. But since we're dealing with triangles, right, these are all going to be positive numbers. Alpha is some angle between, this is going to give us a positive, right, because we are dealing with triangles. So this beta is going to give, the beta we're going to get is going to be between 0 and 90. We're only going to be looking at positive angles. And so if you look at this picture, this angle doesn't fit. So it's going to be giving us this angle here. Okay? So now the question is, how do we go from this angle to discover what this angle is? So now let's take another drawing. I want to take a look at this triangle here. Okay, so I'm going to draw that triangle. I don't need the height anymore. All I need to remember is that that's, let's not mark it with gamma, it's not the same angle, but that point and this point are the same. This is the angle beta. This is the other beta. Let's call it beta star, right? So this, and by this I mean this angle here. Let's mark this a little better. This is beta star, right? This is the angle in there. Beta is the angle in here. That's from here. Okay. Now what we might notice is that these two sides are both A, which means this is an isosceles triangle, which means that this angle here is the same as this angle here. So this is beta in here. Okay, so now looking at this part of the picture, it's clear that beta plus beta star equals pi, or 180 degrees, depending on whether we're in angles or radians. So that beta star is pi minus beta. So when you find your beta, you can get beta star, the other one, using this, right? Maybe I'll put in for the cases when we're dealing with degrees, okay? So in the next video, I'll do an example of this, but this gives us the basic setup and how to determine when we're in one of these cases, okay?